Today's episode dives into three striking ideas shaping modern AI: symbolic superoptimization for tensor programs, a more stable path to 3D policy learning, and a new way to make sign language translation think before it speaks. From faster kernels and stronger robot control to latent reasoning over human motion, these papers show how smarter structure, not just bigger models, can unlock major gains. Stay with us as we unpack what these breakthroughs mean and why they matter. Let's explore the first paper, Prism Symbolic Superoptimization of Tensor Programs. Prism is the first symbolic superoptimizer for tensor programs. Its core contribution is S-graph, a hierarchical representation that keeps the computational structure concrete while leaving execution parameters such as grid, block sizes, and tensor-to-thread mappings symbolic. This shifts optimization from brute force enumeration over concrete graphs to a two-stage process: search over symbolic program families, then instantiate and auto-tune only the surviving candidates. During generation, Prism prunes invalid branches with symbolic dimension matching and expression-guided pruning. The latter evaluates feasibility under a concrete unit parameter assignment and then applies Mirage-style sub-expression checking. Correctness is verified without fixing shapes by translating both the input program and candidate S-graph into tensor expressions and proving equivalence with E-graphs under about 70 algebraic axioms covering operators such as matmu, sum, part, comb, red, and repel. The implementation reuses Mirage's CUDA lowering, adds roughly 6,000 lines of C++ plus 550 lines of Rust, and profiles kernels on NVIDIA A100 GPUs. On 5 LLM workloads, RMS Norm MLP, Swigglue, Attention, and QK Attention Prism reports up to 2.2 times faster kernels than the prior best superoptimizer, Mirage, and up to 4.9 times over compiler baselines, including PyTorch 2, .5.1, Torch.com, Pile, and TVM Ansor. It also cuts end-to-end optimization time by up to 3.4 times, with especially large gains on RMS Norm MLP, where Mirage times out at 3,600 S per configuration, while Prism completes search in 871 S. The novelty is not a better local search heuristic, but a symbolic representation that makes the search space structurally enumerable and soundly prunable. Let's explore the second paper, R3D, Revisiting 3D Policy Learning. R3D argues that 3D policy learning has been bottlenecked less by representational limits than by unstable optimization. On RoboTwin 2, the authors show that DP3's apparent failure to scale comes primarily from batch normalization and missing 3D augmentation. Swapping BN for layer norm turns a uni 3D style encoder from 0% average success to 64.7%, and adding point cloud augmentation stabilizes training curves while raising performance further. They then replace DP3's global feature FILM decoder with a spatially dense transformer diffusion stack, a layer norm only point cloud encoder based on point SAM, uni 3D patchification with FPS and KNN, followed by a diffusion transformer that cross-attends to per-point geometric tokens instead of a pooled latent. The encoder can be pre-trained on ScanNet, ARKit scenes, and PartNext, which improves convergence and transfer. An auxiliary head jointly denoises end effector poses and joint actions with a causal attention mask, improving proprioceptive grounding without contaminating the primary control stream. Empirically, the method reaches 83.8% average success on RoboTwin, 2easy versus 73% for ManiFlow, and 64.8% on hard versus 61.6%. On ManiScale 2, it averages 55.2%, outperforming DP3 at 23% and ACT plus PonderV2 at 42.4%. In real-world experiments on an XARM6 with 2 Intel RealSense D 435 cameras, it achieves 68.7% average success across place kettle, open drawer, and fold towel, compared with 52% for Pi0, 47,3% for ManiFlow, and 40,7% for DP3. The paper's core novelty is the claim that 3D imitation learning becomes scalable once dense spatial tokens, line-only training, and segmentation pre-training replace global pooling and BN-centric design. Let's explore the third paper, Think in Latent Thoughts, a new paradigm for gloss-free sign language translation. Think in Latent Thoughts, or sign thought, reframes gloss-free sign language translation as cross-modal reasoning rather than direct video-to-text mapping. The core novelty is a latent chain of thought module that converts dense, signed video evidence into K-ordered thought slots, then uses a plan-then-ground decoder, first attending to latent thoughts for semantic planning, then retrieving frame evidence for lexical realization. The thinking stage is made structurally stable, with causal self-attention over thoughts, soft temporal segmentation into M-segment tokens, sinkhorn normalized thought to segment binding, and routed cross-attention to encoder features. Two regularizers enforce monotonic course-defined progression and contiguous evidence allocation. A thought-derived temporal prior is also injected into decoder grounding attention, improving evidence faithfulness without changing model I/O. The paper also introduces LCHKSLT, a new Hong Kong Sign Language dataset built from broadcast-style public briefings containing 1,311 hours and 432 K-clips with only sentence-level supervision. The full collection spans 14 signers and a 125,833-word phrase translation vocabulary. On 5 benchmarks, PHO, ENIX1, 4T, CSL Daily, How to Sign, OpenASL, and LCHKSLT, SignThought is consistently strongest among gloss-free methods, reaching 27.22 BLEU, 4 and 54.5 Rouge on Phoenix 1, 4T, 23.92 BLEU, 4 and 50.99 Rouge on CSL Daily, 13.39 BLEU, 4 and 38.1 Rouge on How to Sign, 19.55 BLEU, 4 and 38.78 Rouge on OpenASL, and 21,15 Blue, 4 and 47,87 Rouge on LCHKSLT. Ablations show the latent thinking module is the largest contributor. Removing it drops Phoenix 1,4T Blue, 4 from 27.49 to 25.3. The authors argue the main contribution is replacing opaque direct alignment with explicit latent semantic planning for gloss-free SLT. That's a wrap on today's AI paper highlights. Thanks for watching.